All right, so what I have on the board right now is the chain rule, and you can see that the way it's actually set up in this original function is h of x is equal to f of g of x. And what that means is that you have a function inside of another function. That's when we want to use the chain rule. So in this case, we have the function g of x inside of the function f of x. And so the way that we would take the derivative is we want to take the derivative of the outside part, so that's the f of x function, and we leave the inside alone. Notice that this is still g of x, unchanged, untouched, right? So we took the derivative of the f part, so we have f prime, and on the inside we left g of x alone, and then we multiply by the derivative of the inside, so times g prime of x at the end there. And this is important because what actually happens when you have a function inside of another function is it affects the way that a function changes, or the way that the slope changes on a function, okay? So and a good example of this would be if we said right now, let me just give you a simple example. If f of x is equal to cosine of x and g of x is equal to x cubed, and we want to find f of g of x. Right, so we want g of x to be put inside of f of x. So what I'm going to do is I'm going to take, g of x is x cubed, so I'm going to change this to f of x cubed. And so now if we look at the f of x function, now everywhere that there was an x, we're going to put this x cubed. So I'm going to write out cosine, and then we hit the x, right? But now instead of x, I'm putting x cubed. Okay, so here's our new function. Let me just call this function h of x, right? So h of x is our function, cosine of x cubed. So you can see we have one function inside of another function, right? X cubed is inside of cosine. And those are the times when we want to use the chain rule. Now, this could happen in a variety of ways. So let me just give a couple other examples of a function being inside of a function. Another one would be if we had something like this. F of x is equal to x to the fourth plus 3x plus 2 all squared. Okay? So now what's happened is this thing on the inside right here is a function in and of itself, and then the squared is the other part, right? So that's x to the fourth plus 3x plus 2 is inside of the squared function, okay? So if we wanted to break this into a composition of functions, we could start by saying that h of x is equal to x squared and g of x is equal to x to the fourth plus 3x plus 2. And then what we would have here would actually be h of g of x, right? H would be, g of x would be this stuff, x to the fourth plus 3x plus 2. And so h of this stuff means we put it in, into this function everywhere there's an x. Well, there's an x in the start, so we put all of this down. So x to the fourth plus 3x plus 2. And then this x was squared, so we square all of that stuff, right? So you have one function inside of another. Now, it won't be necessary for you to be able to it won't necessarily be something that you have to do to break them apart like I did right there. But it is good to be able to recognize that this is inside of that, right? You're looking for something to say, hey, this function is inside of another function, so that we can then actually use the chain rule, okay? So let me come, I want to move this one down here. We actually want to take the derivative of this thing right here, okay? And we're actually going to use something called U substitution, okay? So you may want to write that down in your notes, U substitution. No, U as in the letter U, just a U, yeah, the letter U only. You will be doing the U substitution, but it is just U substitution, right? U substitution. So what we're doing whenever we use U substitution is we actually just want to take out one of the functions, okay, to make this thing a little bit easier, to simplify this down, okay? So if I were to look at this function right here, h of x is equal to cosine of x cubed, and I said, hey, what's on the inside right now? What would you tell me is on the inside? Very good. The x cubed is on the inside. So I'm going to pull it out, and I'm going to call it u. I'm just going to rename it, and I'm going to name it u. And I'm going to say that u is equal to x cubed. And all I'm trying to do right now is kind of pull these functions apart so that I can actually I want to use my chain rule, right? If I use the chain rule here, notice that we're going to take f prime of g of x times g of x, right? So we're going to take the derivative of the outside, leaving the inside alone, and then multiply by the derivative of the stuff on the inside. So this will be a new concept, right? So now what I have is that h of x is equal to the cosine of, now you would say x cubed, but I pulled that x cubed over here to the side and I called it u, right? So now I'm going to call this cosine of u. I'm going to call this cosine of u. Now, the derivative here is pretty simple then. H prime of x is equal to, what's the derivative of cosine? Yeah, so the derivative of cosine u is negative sine of u. So what the chain rule allows us to do is we can just take the derivative of that outside piece, right? That was the first part up here. We said we wanted to take the derivative of the outside piece, leaving the inside piece alone. But then the only thing that the chain rule requires us to do is to multiply by the derivative of the inside piece, right? So I'm going to come down here, and I'm going to multiply by the derivative of the inside piece, which is, the derivative of u with respect to x is equal to 3x squared. So over here, I need to be multiplying by the derivative of u with respect to x. This was the last piece of my chain rule, right? So the derivative of the outside, leaving the inside alone, so I just left my u, times the derivative of the inside, so I have my du dx over here. Okay? So now all I'm going to do is I'm going to come back, and I'm going to plug in and finish this thing out. So negative sine of u. Now what was u? X. Yeah, u is x cubed, right? So I'm just going to plug x cubed in for u times du dx, which is 3x squared. And then for simplicity's sake, I'm just going to move the 3x squared to the front. So it'll be negative 3x squared sine of x cubed. And that is the derivative, right? And this is necessary because of the way, this x cubed inside of the cosine function that we started off with is going to have some effect on the slope. And then the cosine is also going to have an effect on the slope. And when you start putting functions inside of one another, their effect kind of gets compounded is the only way I can describe it, right? So the effect begins to grow because you're going to change that x value a little bit. And you're not just plugging it straight into the cosine function when you do that. When you change the x value a little bit, the first thing you have to do is cube it. And then put that new function that's already been changed by the cubed into the cosine function. And then it changes it even more, right? So your changes get compound. And so that's why we multiply the changes together. So, the first part is the derivative of the outside. The second part is the derivative of the inside. And so the changes that each of those pieces bring about end up kind of compounding on one another. Okay, Landon. Yeah, the only reason I'm using the u is to simplify things. Okay, so here's another important concept behind the chain rule. Okay, what I'm really doing is if I have y equals some function. Okay, and I'm gonna let me just call this one. I'll just use sine of x squared this time. Okay, whenever I make my u substitution, and in this case u would be x squared, now I have y equals the sine of u. Okay, so when I actually take this derivative right here, the derivative of this right here, if I was going to name it, it would actually be the change in y with respect to what variable? Yeah, it would be with respect to my u. Okay, so that's the first part that I'm taking whenever I do the chain rule, is my change in y with respect to u, right? And now, when I come over here and I take my derivative of u, it would be the derivative of u with respect to what? With my x, yeah, just because my letters have changed. And remember, we multiply those two things together, the change in the outside times the change of the inside. So these two different derivatives actually end up getting multiplied together. Well, notice what happens when I multiply dy du times du dx. Very good. The du's will cancel, and it will actually give me the derivative of y with respect to x, which is what I would really want if I started here. Notice my variables are in terms of y, and they are in terms of x. So I would be looking for dy dx. But by doing the u substitution and trading the things out, then what I can do is I can actually turn this, instead of one complicated derivative, I can turn it into two simple derivatives that are then multiplied together to give me the end result that I want. You see what I'm saying here? Okay, so this right here, this derivative would be dy du would be equal to cosine of u, a very simple derivative, right? The derivative of this right here, du dx, would be equal to 2x. And then as a result, I can multiply these two derivatives together. So cosine of u times 2x, right, for each of these pieces. And it actually gives me a way of getting a complex derivative. This is dy dx. And then in order to get everything in terms of x, I just need to take the fact that u is equal to x squared and plug it in. So cosine of x squared times 2x. And so now I have dy dx. I have the derivative of y with respect to x. So what it's let me do is break this thing apart using a u substitution, right? And now I can take two very simple derivatives instead of one complex derivative. Does that make sense? Yeah? Okay. Good. So that's all we're trying to do here, right? Because when you have something inside of something else, it makes things complex. And so doing a u substitution lets us break it into two easy ones rather than one difficult derivative, okay? Now, I will say this, because David asked a very valid question a minute ago. U substitution is also used in other things. And in particular, whenever we get to integrals, it will be important that you can do a u substitution, okay? So u substitutions are going to come back around. So doing them right now is going to be important. And then we'll get to some shortcuts later on. But they're not shortcuts like the difference between the definition of derivative and then the power rule. It's just a way for you to be able to work the problem a little bit quicker. But understanding this first is paramount, okay? It's very important. All right, so let's look at another one together. Let's do this one. Y is equal to the square root of x to the fourth plus 1. All right, so if I was going to ask you right now, what's on the inside, what would you say is the interior part of this function? Okay, so that's what I'm going to let be my u, is the x to the fourth plus 1, because it's on the inside, right? So now y is equal to the square root of u. So what is dy du? What's the derivative of this y function now with respect to u? Yeah, 1/2 u to the negative 1/2. Because remember, when you see that square root, you need to automatically think 1/2 power, right? A square root is the same thing as a 1/2 power. So if this was a 1/2 power, we could just use the power rule and be finished, okay? Now, what's the derivative of u with respect to x? Yeah, that derivative is 4x cubed. And now remember, what I'm going to do is I'm going to take dy, what I really want, right? The whole thing of this problem is trying to find dy dx, okay? Well, I have a dy du and a du dx, so what I'm going to do is I'm going to multiply them together. My change in y with respect to u times my change in u with respect to x. And if I do that, then you can see my changes in u will cancel one another out. And I'll get my change in y with respect to change in x. So let me actually do that. Change in y with respect to u is right here. It's 1/2 u to the negative 1/2 times my change in u with respect to x is here. It's 4x to the third power. That's exactly right? I want this thing, I don't want a u anymore, so what I'm going to do is I'm going to trade it out. U is x to the fourth plus 1. So where it says u, I'm putting in x to the fourth plus 1, now to the negative 1/2 power, times my 4x cubed. And this can be simplified, okay? I always like to take my constants and multiply them together. So here's a 4 and a 1/2. So if I multiply those together, what am I going to get?
2.
Yeah, that'll be 2. And then I'm going to go ahead and carry my x cubed to the front just because I like the way that looks, right? And so I would call this the clean version of it, right? I multiplied my constants together just to get one constant in the front. And then I have my x cubed up there as well, just because I like to move those to the front. I think it looks better, right? Does anybody have any questions at this point? It is. It's a really clever idea, taking those two simple derivatives and multiplying them together to make, one complex derivative. It's nice and easy. All right, so since everything is being multiplied together in this last step, I can, remember, if you have things being multiplied together, you can multiply them in any order. 2 times 3 times 4. Do the 2 and the 3 first. Times 4. So that's 24. All right, now do 2 times 3 times 4, but do the 2 and the 4 first. All right, and then 8 times 3. So when it's called the associate. That's the idea. Oh, man. Straight up 25. Yeah, 24 is actually the correct answer. But it doesn't matter the order, and that's actually the associative property of multiplication, right? So all I did was I chose to multiply that and the 1/2 together from the very start. And 4 times 1/2 is 2, and then the x cubed just stays. So that's where the 2x cubed came from. And then I just moved it to the front, okay, and then multiply. All right, so here's another one we can work. Y equals 7x squared plus 2x plus 4 to the negative 1/3 power. All right, what's on the inside? So my u is going to be 7x squared plus 2x plus 4. So now I have y is equal to u to the negative 1/3 power. Remember, I really want dy dx. I want the change in y with respect to my x value. So I'm going to take two derivatives. I'm going to take the change in y with respect to this u right here, and that's going to give me negative 1/3 u to the negative 4/3. Then I'm also going to take the derivative of my u over here. So the change in u with respect to x is equal to 14x plus 2. And I'm going to multiply those two derivatives together. dy du, change in y with respect to u, times my change in u with respect to my x. And my changes in u will cancel. And if I can see if I multiply those two derivatives together, then what will happen is I'll end up with my change in y with respect to x. So I'm just going to multiply them together. Negative 1/3 u to the negative 4/3 times 14x plus 2. And now I want everything in terms of x, so I'm just going to use the fact that u is equal to 7x squared plus 2x plus 4 and plug it in. So negative 1/3 times u is 7x squared plus 2x plus 4. And all of that is now to the negative 4/3 power times my 14x plus my 2. No, you don't have to change it to a U. That's a valid point, right? It's good practice for you to start distinguishing what is on the inside and what is on the outside, but you don't have to. We'll actually work some in a little while where I won't make you actually change them into a U, okay? But we want to practice with it primarily because it's going to be really important whenever we do whenever we start doing integrals, that you be able to recognize a U and the whole concept behind the chain rule, okay? Yeah, you really could. You could always do the chain rule, but the only thing is you might end up multiplying by a 1 a lot, or you may end up, it's just like you could use the product rule with 2x, with the derivative of 2x, right? It's just going to be a lot of wasted, yeah, because f prime of x, if you did the product rule, would be the first times the derivative of the second plus the second times the derivative of the first. Oh, and that's going to cancel, and then you still just get 2, right? But the product rule still works, right? And so you could end up doing the same thing with the chain rule. It would still work. You just might end up, doing more than you really need to. Okay, here's another good one. Y equals e to the cosine t. Okay, so e to the power of cosine t. Yeah, we'll just use the t, just for fun. Right, so what we're looking for right now would be our change in y with respect to t. That's what we want, right? Change in y with respect to t. Okay, now you may want to make this distinction in your notes, okay? Whenever you have e to something, you have e raised to some, function or whatever, I always ask you what's on the inside? What's on the inside, right? That's been my continual question. Well, the top is the inside. Okay, so you may want to just make that note because people always say, I wasn't sure what the inside was, right? Whenever you have e to some power, the top is the inside. So when we're trying to do our U substitution and I look at you and I say, what's on the inside of this function? Well, on the other ones, it's been blatantly obvious. Look, there's a parentheses, and there's something inside of the parentheses. Hey, look, there's a square root, and there's something inside of the square root. Hey, look, there is a trig function, right? There's a trig function, and there's something in parentheses inside of the trig function. And then we get down here to this one, and I say, what's on the inside? And everybody panics, right? Because there's no obvious inside, but the top is the inside. So U will be equal to cosine t. So Y is equal to e to the U. So dy du is going to be what? Yeah, e to the U. Now my change in U with respect to t is going to be negative sine t. Very good. And now I just need to multiply those two things together to get change in y with respect to t. So e to the u times negative sine of t. Notice I'm putting that negative sine of t in parentheses because I want you to know I'm multiplying it. I'm not doing e to the u minus sine. Now e to the u, well, I can trade that u for cosine of t negative sine of t, right? And all I did here was I moved that negative from the sign to the front down here, okay?
So really, whatever you put the U, you're only putting that U there just to let you change whatever, and that's just to go to our
Mhm. I'm only taking the u, taking that thing out and making it a u to simplify this derivative right here, just to make that derivative easier to look at. And then I need to get it back in there. Yes. So now I just need to make sure that I can get it here to, take a really simple derivative. But I actually want it in terms of t because I'm looking for dy dt in this case, changing y with respect to t. So that's why I want to get the cosine t back in here because I want this thing in terms of t. I don't want u's and t's in my final answer. I just want t's. Okay. Okay, so let's do one that is a little more complex. Let's say that f of x is sine squared of 5x. That was not bad. Now, here's what I want you to think about. When I say what is on the inside, I don't want you to think of like the smallest one on the farthest inside. Does that make sense? Imagine having like 5 boxes and one of them inside of the other, okay? When we do the chain rule, we actually just want to unpeel it one layer at a time. So you don't want to go in and immediately grab the smallest box, okay? So if you're trying to pull these boxes apart, what you actually want to do is you want to get the next biggest box that's not the one on the very outside, okay? So if you're looking at this, what is actually on the very outside right now? The squared is, yeah, because we had this discussion earlier, right? Sine squared of 5x is the same thing as sine of 5x all squared. And so now when if you see this, you need to think of it in your mind as this right here, okay? You need to think of it as that squared is really on the outside. It's big. It's the alpha dog, right? It's the one that is actually covering everything else up. Okay? It's the largest one. So when you look at this right here and I say what's on the inside, remember, I don't want you to go for the small box in the middle. I want you to go for the next biggest one, right? Yeah, so our u is going to be sine of 5x. So f of x, and actually let me use y's instead of f of x. It's going to make a little demonstration I'm going to do in a minute easier if I just go ahead and use a y. So y will be equal to u squared now, right? But now let me draw your attention to my u. What do you notice about my u now? Yeah. Very good. It's a function inside of a function. Because now the 5x function is where? Inside of the sine, right? So in order to take the derivative of u, what am I going to have to use? A chain rule, right? So I'm in my u over here, and I actually need to pick a u for my u function. Yeah, it just makes a chain, right? And if there were 6 of them, you could have, this is actually called a 3-link chain, and then we could have you could make a 6 or an 8-link chain if you wanted to. Okay, we may do it for fun one day. All right, so now I have to pick a u inside of the u that I already have. So what's on the inside in the u function here? What's on the inside? 5x. Now, am I going to call it u? No, I've already used u, right? So if this is, I got to pick a u within a u, guess what I'm going to call it? No, a double u. Yeah. See what I did there? Okay. So that one's going to be double u. So now u I can actually change into sine of w. You're welcome. One of my favorite mathematical jokes that I get to make every year. It's a fantastic pun. I really do look forward to making mathematical jokes every year. Okay, So now I want you to see what we're doing. So now we have everything broken down. There's, nothing. So there's nothing inside of anything else here, nothing on the inside here, and there's nothing on the inside here, right? All of these things are broken down to where it's just a simple function by itself. And if you did talk about the derivative of the insides, they would all be 1, right? So there's nothing major going on in any of these. So now I want to take all of my derivatives. What's the derivative of this y with respect to u? That's 2u. Okay. What's the derivative of this u with respect to w? Very good. It's cosine w. And what is the derivative of w here with respect to x? It's 5. Now that I have a 3-link chain, guess what I'm going to do with all the answers? Yeah, because watch what happens. I'm just going to give you the notation here. If I multiply all of these together. Right? My changes in u cancel. My changes in w cancel. And my end result is simply my change in y with respect to my change in x, right? And so we can make these chains go on and on and on if we need to, and they will always just give us the change in y with respect to x. Okay, so I'm going to multiply them together. dy du is 2u. Change in u with respect to w is cosine of w. And the derivative of w with respect to x, 5. Now remember, in my final result, I don't want a w and a u, right? I just want x's everywhere. So I'm going to go back and I'm going to plug in for w. W is equal to 5x. So I'm going to have cosine of 5x times 5. And then over here, 2u, I'm going to go back to the top, right? U is equal to sine of 5x. So for this u, I'm putting sine of 5x. And remember, just to clean things up for the end, I want to multiply my constants together. So there's a 5 and a 2. So 5 times 2 is 10 times sine of 5x times the cosine of 5x. That's my derivative.